Assalamualaikum and hello everyone. Today our group 11 will present about our project where we were assigned to manufacture an automotive industry product or automotive component. So our group choose internal combustion engine piston. So our group consists of three participants, which is Muhammad Hanif Hakim, Muhammad Irfan and me, Fakrul Iman. Without further ado, I will start with our project overview, which is the introduction of internal combustion engine piston. So, what is the function and mechanics for internal combustion engine piston? So, the first one is combustion boundary. It serves as a dynamic moving seal inside the engine cylinder to construct a perfectly closed combustion chamber. So, the second one is incredible stress resistant. This engine piston can withstand brutal cyclic gas pressure up to 10 MPa, which megapascal, and extreme thermal shocks exceeding 2000 degrees Celsius. The third one is the energy transfer. For the engine This engine piston system, it directs explosive gas expansion forces to the gudgeon pin directly to the connecting rod, spinning the crankshaft. Here is the technical schematic of internal combustion engine piston. And then the last one is blow by prevention system, which is it incorporates structural ring groove to retain compression and oil control rings, keeping exhaust gases out of the crankcase. So how are these internal combustion engine pistons are produced? The first one is mass production system, which is its automated dedicated flow line setup. Since automotive pistons are standardized high repetition components, our facility layout implements robust manufacturing automation. Automated robotic arms perform critical mode pouring, integrated cooling, convenience regular crystallization, and high precision CNC cells perform rapid, repeatable final machining. Because of the mass production system, the production target is 1,200,000 units annually. It's designed to supply top-tier standard four-cylinder passenger vehicles lines with approximately 300,000 completed automotive engines per year. So the operating scales are 3 shifts per day, 5 days per week, and 50 weeks per year. So about the daily yield rate, it's approximately like 4,800 units per day or 200 parts per hour. But how about the production cost for internal combustion engine piston? So the cost component breakdown consists of direct material, like we use premium alloy AA4032. Uh, so per unit it is $3.50. And then we have direct labor like foundry technicians, CNC operators, and QA staff, which is $1.50 per unit. And then manufacturing overhead like tooling wear, CNC depreciation, natural gas, we use $4 per unit. And quality control and packaging, automated NDT X-ray, secure shipping crates, and it is for $1 per unit. And we add up to the total estimated manufacturing cost per unit is $10.
Moving on to section 2, let's look at the design and material strategy that underpins our entire manufacturing system. When engineering a high-performance internal combustion engine piston, choosing the right material and the ideal fabrication method determine both operational survival and market competitiveness. For our project, we selected the premium aluminium silicon alloy, which is AA4032. These materials offer three distinct engineering merits that make it perfect for our application. First, low expansion. By integrating 11 to 13% silicon, a dense array of primary silicon crystal is formed. This aggressively lowers the piston thermal expansion, ensuring it doesn't seize inside the cylinder at high operational running temperature. Second, optimal inertia. AA4032 has a density of only about 2.7 gram per centimeter cube compared to the traditional cast iron, which sits around 7.2 gram above centimeter cube. This drastically cuts down the reciprocating mass. This enhances fuel efficiency and minimalize wear on the crankshaft. Third, superb heat transfer. Its high thermal conductivity rapidly channels intense combustion heat away from the vulnerable piston crown over to the cool cylinder walls, preventing dangerous pre-ignition hotspots. But material selection is only half the battle. We also had to determine how to shape it. We evaluated three competing manufacturing processes, which is gravity die casting, mechanical forging, and high pressure casting. While mechanical forging yields maximum strength and zero defects, its geometric capability is poor for complex hollow designs and the tooling costs are exceptionally high. On the other hand, high pressure casting provides excellent thin wall geometries, but it introduces high internal porosity defects. Ultimately, we choose gravity die casting. It strikes the ultimate balance for our project, which is it keeps internal defects low, permits internal core for complex geometries, maintains affordable tooling costs, and provides the outstanding mass scale suitability needed to hit our annual target. To bring this design to life, our production layout transitions through four process manufacturing stages. First, foundry and cast. AA4032 ingots are melted in gas reverberatory furnace at approximately 720 degrees Celsius. Automated robotic arms then pour the molten alloy into preheated tool steel molds. Second, T6 heat treatment. To unlock the material mechanical strength, the cast parts are solution treated at 500 degrees Celsius, polymer quenched and artificially aged to precipitate key hardening phases. Third, CNC machining. Next, high precision multi-axis CNC center turns the outer profile, slice process piston ring groove, and bore the crucial gudgeon holes. And lastly, surface and quality. Finally, the piston skirt receives a screen printed graphite anti-friction coating and an automated industrial X-ray inspection scans the part to completely rule out the subsurface porosity. To execute this workflow at a massive scale of 1.2 million units a year, our facility relies on an advanced machinery portfolio. For casting and thermal treatment, we utilize a 10-ton gas-fired reverberatory furnace equipped with integrated multi-port rotor degasser that use nitrogen gas to purge trapped hydrogen from the melt pool. This is paired with an automated match belt continuous T6 furnace system that carefully coordinates heat ramps and drop quenching for uniform hardness. For machining and inspection, we deploy multi-axis CNC lathe that perform advanced turning and milling in a single setup, eliminating dimensional stacking drift and boring the wrist pinhole to a strict tolerance of plus minus 0.05 mm. Finally, our quality system features automated screen printing structures and automated X-ray scanner to validate surface coating and structural integrity. Precision is guaranteed by implementing rigid geometric dimensioning and tolerancing, or GD&T, standard across three critical parameters. Cylindricity control, we restrict the outer piston skirt variation to within 0.015 mm. Maintaining this ideal run cross-section guarantees an optimal lubrication oil film thickness, eliminating localized scuffing and piston slap. Perpendicularity control, applied to the gudgeon pin bore at a tolerance of 0.01 mm relative to the secondary datum axis. This ensures the wrist pin lines up perfectly straight, preventing uneven side loops on the connecting rods. Lastly, parallelism control. Held to within 0.02 mm on the compression ring groove relative to the lower skirt face datum. This torque brings flutter and ensure long-term pressure ceilings. By utilizing these optimal cylindrical datum zones instead of standard linear dimension, we achieve a 57% expansion of our manufacturing acceptance target zone without sacrificing part assembly or performance. To close up section 2, let's look at how we engineer sustainability into this process. Our ecosystem thrives on a clean, green manufacturing loop. First manufacturing loop, scrap shavings and gates account for 30 to 40% of our material costs. We press the CNC chips into briquettes and remelt them in-house, cutting our manufacturing energy consumption by 95% compared to mining raw bauxite. Secondly, heat recovery. Our system utilizes recuperative burners that capture extreme waste heat from the gas-fired exhaust, channeling it back into the furnace preheating lines. This reduces our facility's overall gas demand by 15 to 20%. Lastly, eco-fluids. Finally, our machining centers rely on biodegradable synthetic vegetable-based lubricants rather than petroleum coolants. This spend oil continuously clean and recycle using a fast centrifugal separator, giving us a highly efficient and environmentally responsible footprint. Thank you.
To wrap things up, let's look at the big picture of our initial combustion engine piston manufacturing project. In conclusion, our proposed gravity die casting manufacturing layout offers a robust, financially highly lucrative, and environmentally sustainable system for high volume automotive piston production. By achieving a strong profit margin of $10 per unit, this layout proves that we do not have to compromise on economic viability to meet modern sustainable standards and highly volume demands. We are confident that this system strikes the perfect balance for long-term operational success. Thank you so much for your time and attention today.